Hi, I'm Petr Krysl and I use Julia for prototyping algorithms and for implementing computations in ad hoc simulations for applied science projects, for instance, hearing in marine mammals. This account is intended for researchers who are looking to Julia to boost their productivity. So, by no means for Julia experts, but rather the novices. This account is not complete and I do not have supporting data. It consists mostly of personal experiences. I would like to point out that there's an organization, Julia PDE, which demonstrates that the Julia environment for solving partial differential equations is quite rich and reasonably complete, be it solvers, libraries for building simulations, or application packages. There's probably little that is missing. I came to Julia for speed. The ability to produce fast code was, and still is, prominently featured in Julia documentation. It is really nice to have a fast language that can be used to write everything. So here I show the so-called acoustic color graph, which is obtained by circling around a scatterer underwater and also sweeping through frequencies at the same time. The model is coupled finite elements and boundary elements, and it tends to be expensive. Each column in the image towards the right, that is for high frequencies, tends to take hours to complete. And I can use Julia from the Green's function microkernels through operations on big complex matrices to the overall structure of the simulation and management of the data. This is all nice, but what really impresses me these days is something else. Julia is somehow able to increase my productivity by being consistent, easy to read, and flexible. I have done some work with C++. I don't think I would have been able to complete the code without the debugger. Moving on to MATLAB, I thought that being high level, it would be a step up from C++, but somehow I still spent my days in the debugger. About 3 years ago, I committed to Julia. The other day, I realized I haven't needed the debugger once in all those years, despite having programmed some 100,000 lines of code. I had to do a mental double take when I realized that it was quite shocking. Here, you will recognize the classical example of the linear heat conduction, bilinear and linear form evaluation from a Galerkin finite element model. With a little bit of care, one can write code that doesn't really require any explicit type annotations. The compiler can figure it out on its own. In combination with static arrays, one can get very clean and at the same time high performance code. So both fast and easy to read. But asking for performance may run into some language limitations. Take, for instance, MATLAB. While the code doesn't look very different, it is in fact quite a bit more complicated. The developers had to reorganize everything into arrays so that vectorization could be taken advantage of. Without vectorization, the performance would have been horrible. So the look of the code may on surface not be that different, but it is easy to see how a debugger might be required to make it work due to all those multidimensional arrays. Here's the same assembly procedure implemented in C++ in the well-known Deal2 finite element code. Note that this was supposed to be easy to read, being part of a tutorial for beginners. I think that this clearly shows that the explicit requirement of typing everything can really get in the way of understanding what's going on. Just compare the length of the codes and the amount of black ink. Here's another example, this time not my code, the Seagull geometric library in Julia on the left and the C++ on the right. Julia is not object-oriented, which in my opinion is a good thing. It leads to a different view of how to design the code. Here's an example. Some finite elements do not have the ability to evaluate the geometry. for instance, L2 elements with interior basis functions. They need a proxy, a geometry carrier, that will do that for them. In C++, the natural thing to do would be to store a reference to the geometry carrier in the data structure for each finite element. In Julia, the focus can be redirected to behavior. Simply ask the finite element who its geometry carrier is. Most finite elements would reply that they are their own geometry carriers. This is expressed in a really inexpensive way as a function that simply returns the argument. Those finite elements that do require a proxy can then override the above generic function to request assistance of a different finite element. Another habit of C++ users tends to be to view everything as objects. When building mesh libraries, everything is then an object. Because C++ objects are implemented essentially using pointers, this would then tend to use a lot more memory than necessary. For instance, even when the indexes themselves are stored as 32-bit numbers, the pointers are typically 64-bit. Julia makes it easy to think at the right level of abstraction. In the case of the mesh core library, that happens to be the incidence relation. When the incidence relation has a fixed cardinality, and the short vectors of the fixed cardinality are stored as static arrays, the compiler is then clever enough to eliminate any and all pointers and store everything in one contiguous array. Thus, for instance, storing the entire full one-level mesh hierarchy, we can use up quite a bit less memory than the next best database. Storing the up-down reduced links only between the vertices and the elements, the Julia library again consumes considerably less memory than the comparable databases in C++. Saving on memory is great, but designing at the right level of abstraction also has the advantage of providing the user with a choice which topological relations to store. There's no need to decide beforehand what needs to be stored and encode it in the types that needs to be compiled into a library. These decisions are easy to make on the fly in the Julia design. As you can probably guess, the answer is no. There's definitely more that I like about Julia. Here are a few more things. I find the test-driven development very well supported. That and the continuous integration really help streamline development of packages. Documentation in Julia is so easy that even casual packages tend to have decent documentation. Parallel processing, be it with processes or with threads, is definitely a breeze compared to what I was used to from my C language programs. And there are other things that make using Julia for numerical computing worthwhile. Recently started experimenting with automatic differentiation for constitutive equations. Here are the references. Find tools may be useful if you're interested in prepackaged functionality. It has, for instance, high-performance finite elements for solid mechanics. Mesh Tutor might be useful if you're interested in the mesh database I mentioned in this talk. Elfel is a library of building blocks for mixed finite element methods. The intent was to write it in a way that could deliver both on legibility and high performance. Finally, the Julia PDE organization site may help you find the packages or functionality you're interested in.